Imagine looking up at the night sky from a place with no city lights, no street lamps, no glowing windows, and no haze sitting above the horizon. At first, it feels like the darkness is empty. Then your eyes adjust. One star appears, then another, then hundreds, then thousands. The Milky Way stretches overhead like a pale river of dust and frozen fire. And for a moment, the sky stops looking like a ceiling and starts looking like a doorway. But then comes the question that should feel simple. If the universe is filled with stars, galaxies, nebulae, and billions of suns, why is it dark? Why is most of the sky black? Why does space look like an endless ocean of shadow when every direction should eventually lead to something shining? That question sounds quiet, but it is not small. Because the darkness above us is not just the absence of nearby light, it is evidence. It is a record of time. It is a clue that the universe had a beginning, that light has limits, that distance changes everything, and that most of reality is hidden from human eyes. Before we begin tonight, if you enjoy calm journeys through space, take a moment to subscribe, like the video, and write a comment telling us where you are watching from and what time it is for you right now. It is strange to think that people all over Earth can look into the same sky at different hours, from different places, while the same universe stretches above everyone. Tonight, you are watching the Just About Space channel, talking about the universe is dark for a reason, and it's terrifying. And to understand why the universe is dark, we have to begin with the part of space that feels most familiar, the night. A dark sky feels normal to us because we have lived with it our entire lives. The sun sets, the air cools, the blue fades, the first stars appear. We call that night, and because it happens every day, we rarely treat it like a mystery. But scientifically, the darkness of night is one of the deepest clues in all of astronomy. It is not obvious that the sky should be dark. In fact, for a long time, it was a serious problem. If the universe were infinite, eternal, unchanging, and filled with stars more or less everywhere, then every line of sight should eventually end on the surface of a star. Look straight up, and if you go far enough, there should be a star. Look slightly left, and there should be another. Look between two bright stars, and the black gap should not really be empty. If space went on forever, and stars had always existed, that gap should eventually be filled by the light of another sun farther away. And if that were true in every direction, the night sky should not be black. It should blaze, not with scattered points of light, but with something closer to the surface of a star stretched across the entire heavens. This is the old problem known as Olbers' paradox. It asks why the night sky is dark if the universe contains so many sources of light. And the answer is not simply that the stars are too far away. That answer feels right, but it does not solve the real problem. A star becomes dimmer with distance because its light spreads out over a larger area. But as you look farther into a uniform universe, there is also more space, and therefore more stars. The dimness of individual stars and the growing number of distant stars can balance each other in a simple, eternal universe. Layer after layer of stars would keep adding light. A shell of stars nearby would contribute some brightness. A larger shell farther away would contain more stars, each dimmer, but together adding roughly the same amount. Then another shell, and another. If the universe were truly infinite and old enough for all that light to arrive, the total light could become overwhelming. So the darkness is telling us something. It is telling us that the universe is not the simple, infinite, eternal, static sea of stars that people once imagined. It is finite in age. It changes, it expands, and light does not get unlimited time to travel. That is the first reason the universe is dark. The universe has not existed forever. Light from distant places has had only a limited amount of time to reach us. The universe is about 13.8 billion years old. That sounds enormous, and compared with a human life, it is almost impossible to imagine. But for light, even 13.8 billion years is not enough to bring us information from everywhere. Light is fast, but it is not instant. It crosses the distance from the moon to Earth in just over a second. It reaches us from the sun in about 8 minutes. It takes more than 4 years to arrive from the nearest star system beyond the sun. It takes tens of thousands of years to cross the width of the Milky Way. It takes millions of years to travel from nearby galaxies. And it takes billions of years to reach us from the deepest galaxies we can observe. When you look into space, you are not seeing things as they are right now. You are seeing old light. The farther you look, the older the picture becomes. The universe is dark partly because most possible light has not had time to arrive. Some stars may exist beyond our observable reach, but their light has never crossed the distance between them and us. Some galaxies may be real, enormous, and full of suns, but from our point of view, they are outside the region of space that can ever tell us anything. Darkness is not always emptiness. Sometimes it is distance plus time. A black patch of sky may not mean nothing is there. It may mean whatever is there is too far away for its light to have reached Earth since the beginning of cosmic history. That is already unsettling. The dark sky is not merely a curtain, it is a horizon. But there is another reason the universe is dark, and it is even stranger. The universe is expanding. Space itself is stretching. Galaxies are not simply flying through a fixed container, like sparks from an explosion. The distances between large clusters of galaxies are growing, because the fabric of space between them is growing. As light travels across that expanding space, the wavelength of the light stretches too. Visible light can become infrared. Infrared can become microwave radiation. Photons lose energy as the universe expands. So even when ancient light does reach us, it may no longer arrive as the kind of light our eyes can see. The oldest light in the universe is not black. It is everywhere. It fills all of space. But your eyes cannot see it, because expansion has stretched it into microwaves. This is the cosmic microwave background. It is the afterglow of the early universe, the cooled remnant of a time when the cosmos was hot, dense, and filled with radiation. If your eyes could see microwave light, the night would not look empty. The whole sky would glow with a faint, nearly uniform signal from the young universe. But because human eyes evolved to see visible light, that ancient glow is hidden. To us, it becomes darkness. So the dark sky is partly an illusion created by biology. The universe is not completely dark in every wavelength. It is dark to us. Radio telescopes see a different sky. Infrared telescopes see through dust that blocks visible light. X-ray observatories reveal violent objects that our eyes would miss entirely. Gamma-ray detectors catch the most energetic explosions. The human eye receives only a narrow band of the cosmic story. Everything outside that band becomes invisible unless we build instruments to translate it. When we say the universe is dark, we are usually describing what visible light tells us. But visible light is only a small window. Space is full of signals that our bodies were never built to sense. That does not make the darkness less real. It makes it more complicated. Because the universe can be glowing, humming, vibrating, and radiating all around us, and still appear black to a human being standing under the night sky. The darkness is not simply out there. Part of it is inside our senses. Now, before we go farther, we need to separate two kinds of darkness. There is local darkness, and there is cosmic darkness. Local darkness is why space looks black to astronauts even when the sun is nearby. On Earth during the day, the sky is blue because sunlight hits molecules in the atmosphere and scatters. Blue light scatters more strongly than red light, so the whole dome of air above us glows blue. The sky is not blue because space itself is blue. It is blue because air gets involved. On the moon, there is no thick atmosphere to scatter sunlight. An astronaut standing in direct sunlight can see a brutally bright surface below, a blazing sun overhead, and a black sky behind it. The same sun that turns Earth's daytime sky blue cannot brighten the lunar sky, because there is almost no air to scatter its light. In empty space, light travels in straight lines until it hits something. If it does not hit dust, gas, a spacecraft, a planet, or your eye, it remains unseen. A beam of sunlight crossing a vacuum does not illuminate the vacuum itself. It only becomes visible when matter redirects or absorbs it. This is why the sky can be black even close to a star. The photons are present, but without enough material to scatter them toward you from all directions, the surrounding space remains dark. That kind of darkness is about the absence of matter. Cosmic darkness is different. Cosmic darkness is about the entire universe. It asks why, even with all the stars, galaxies, and glowing gas clouds that exist, most of the sky still looks black. And to answer that, we have to think beyond the solar system, beyond the Milky Way, and beyond ordinary distance. The universe is not filled evenly with stars. Matter is clumped. It forms planets around stars, stars inside galaxies, galaxies inside groups and clusters along huge filaments of the cosmic web. Between those filaments are voids, enormous regions of space with very little matter. Some cosmic voids are hundreds of millions of light years across. They are not completely empty, but compared with galaxies, they are astonishingly sparse. If you could place yourself inside one of these great voids, the night sky might be almost unrecognizable. The Milky Way would not be above you. The nearest large galaxy could be unimaginably far away. The sky might contain only a handful of faint smudges, and most directions would look like deep black. The darkness of the universe is partly caused by structure. Gravity gathers matter into islands, expansion stretches the ocean between them. The result is not a universe evenly wallpapered with stars. It is a universe where light collects into knots, streams, and cities, while vast regions remain nearly bare. This is important because the title of tonight's journey says, "The universe is dark for a reason." That reason is not one single fact. It is a chain of facts. The universe had a beginning. Light has a speed. Space expands. Wavelengths stretch. Matter clumps. Stars require special conditions. Most matter does not shine. And most of space is not inside galaxies at all. Each fact removes some of the light that an eternal, static universe would have given us. Together, they explain why darkness dominates the view. But they also reveal something frightening. The darkness is not a mistake. It is not a temporary fog hiding a bright universe behind it. The darkness is built into the way the universe works. To see why, let's go back to the earliest time we can observe with light. The young universe was not dark in the beginning. It was intensely bright, but in a way that no eye could have survived or understood. Shortly after the Big Bang, the universe was a hot, dense plasma of particles and radiation. There were no stars yet, no planets, no galaxies, no atoms in the familiar sense. There was no black sky filled with points of light, because there was no open space like we imagine today. Light existed, but it could not travel freely. Free electrons scattered photons again and again. A photon could move only a short distance before being knocked in another direction. The universe was like a glowing fog, not dark, but opaque. If you had somehow existed inside it, looking far away would have been impossible. Every direction would have ended quickly in hot plasma. Then the universe expanded and cooled. After about 380,000 years, electrons and nuclei combined to form neutral atoms. This event is called recombination, though it was really the first stable formation of atoms on a cosmic scale. Once neutral atoms formed, light could finally travel through space without constantly scattering off free electrons. The universe became transparent. The photons released then are still traveling today. We observe them as the cosmic microwave background. But here is the strange part. When that light was released, the universe would have glowed with the temperature of thousands of degrees. Today, after more than 13 billion years of expansion, that same light has cooled to about 2.7 Kelvin, only a few degrees above absolute zero. Expansion stretched it from visible and infrared wavelengths into microwaves. The earliest light became invisible to our eyes. The first great glow of the universe is still here, but it arrives as cold radiation from every direction. That means the darkness above you is not because the early light vanished. It is because the universe stretched the light until your eyes could no longer receive it. There is something deeply eerie about that. The oldest light in existence surrounds us at all times. It passes through the room around you. It moves through your body. It fills the space between galaxies. Yet without special instruments, you would never know it is there. The universe can carry its first photograph everywhere and still hide it in darkness. After the cosmic microwave background was released, the universe entered a period known as the Cosmic Dark Ages. This name is not poetic exaggeration. For a long time, there were no stars. The universe was transparent, but there were no large sources of visible light. There was hydrogen, there was helium, there were tiny density differences. There was gravity beginning to work. But there were not yet suns, galaxies, or glowing nebulae. For tens or hundreds of millions of years, the cosmos was mostly dark gas drifting through expanding space. This is one of the most important chapters in the story of cosmic darkness. There was a time when the universe was not dark because light could not travel. It was dark because there were almost no objects making visible light. The first stars had not ignited. The first galaxies had not assembled. The cosmic web was only beginning to form from small irregularities in matter. Gravity was pulling slightly denser regions inward. But collapse takes time. A cloud of hydrogen does not become a star just because gravity exists. It must cool. It must gather enough mass. It must overcome pressure. It must become dense enough and hot enough at its center for nuclear fusion to begin. That process turned tiny initial differences into the first luminous structures. But until the first stars were born, the universe had no sunrise. No direction was special. No sky contained constellations. No planet existed to look up. There was only expanding darkness, neutral gas, and the slow growth of structure. This is why the dark universe is not just the far future. It is also the ancient past. Darkness came before the stars. Light is the later chapter. Eventually, gravity won in certain regions. Gas collected into the first halos. The first stars ignited. They were probably very different from the sun. They formed from almost pure hydrogen and helium, because heavier elements had not yet been made in large amounts. Many of them may have been massive, hot, and short-lived. They burned fiercely, produced ultraviolet radiation, and began changing the gas around them. Their light started to break apart, neutral hydrogen, in a process called reionization. The universe slowly emerged from the Dark Ages. The first stars died quickly, and some exploded as supernovae, seeding space with heavier elements: carbon, oxygen, silicon, iron, the ingredients needed later for rocky planets, oceans, atmospheres, and life. From these deaths came the material for future worlds. But notice what this means. The universe did not become bright all at once. It lit itself gradually. first in small patches, then in growing bubbles around early stars and galaxies, then across larger regions as ultraviolet radiation carved through the hydrogen fog. Cosmic light was not a switch. It was a struggle. Even after the first stars appeared, the universe was still mostly dark by volume. Light gathered around sources. The spaces between them remained enormous. This pattern continues today. We live long after the first light, after billions of years of star formation, after galaxies have had time to grow and collide and build grand spirals and giant ellipticals. And still, most of the universe is dark, because even a universe filled with galaxies is not the same thing as a universe filled with light. A galaxy can contain hundreds of billions of stars and still occupy only a tiny fraction of the space around it. The Milky Way is vast by human standards. It is about 100,000 light-years across, but the distance to the Andromeda Galaxy is about 2.5 million light-years. That means the empty gulf between major galaxies can be many times wider than the galaxies themselves. Now, scale that up. Clusters of galaxies are separated by even greater voids. Superclusters trace filaments through the cosmic web, but between them lie regions so large that light itself takes hundreds of millions of years to cross them. The shining parts of the universe are like islands. The dark parts are the sea, and the sea is not a small background. It is most of the map. This is also why the phrase "filled with stars" can mislead us. The universe contains an enormous number of stars, but it does not contain stars everywhere. If you shrank the sun down to the size of a grapefruit, the nearest star would still be thousands of kilometers away on that scale. Stars are not close together in the way grains of sand are close on a beach. They are isolated furnaces separated by oceans of vacuum. Galaxies look dense in telescope images because their light has been gathered and compressed by distance. From far away, a galaxy becomes a glowing disk or oval. But inside a galaxy, stars are separated by huge distances. If two galaxies collide, their stars almost never hit each other directly. There is simply too much space between them. The gas clouds interact. Gravity reshapes the galaxies. New stars can form. But the stars themselves mostly pass through the merger like fireflies crossing through different parts of a dark field. So even inside galaxies, darkness dominates. The darkness is not an exception found only outside the cosmic web. It exists between stars, between planets, between dust grains, and between atoms. If you could remove every planet, every moon, every asteroid, and every spacecraft from the solar system, almost all of its volume would still be empty. The Sun holds nearly all the mass, but the planets orbit far apart. The solar system is not a crowded clockwork machine. It is a central star surrounded by enormous intervals. Neptune is about 30 times farther from the Sun than Earth is. The Kuiper Belt stretches beyond Neptune. The Oort cloud may extend thousands or even tens of thousands of astronomical units from the Sun. And yet even that enormous realm is still part of one star's extended neighborhood. Beyond it lies interstellar space, then other stars, then the wider galaxy, then the gulf between galaxies. At every scale, space is larger than matter. That is one of the reasons the universe is dark. There is simply more room than there are lamps. But this still leaves a deeper question. Why is there so little matter compared with space? Why is the universe not denser? Why didn't gravity pull everything into stars everywhere? The answer takes us into the early universe again. The structure we see today began as tiny differences in density. The universe was remarkably smooth when the cosmic microwave background was released. Not perfectly smooth, but close. Some regions were slightly denser. Others were slightly less dense. Gravity amplified those differences over time. Slightly denser regions attracted more matter, becoming even denser. Less dense regions lost matter and became voids. Over billions of years, this process built the cosmic web. But because the early universe was expanding, matter did not simply collapse everywhere at once. Expansion competed with gravity. Small regions could collapse if their gravity was strong enough. Large-scale expansion continued stretching the distances between structures. The result is a universe where matter forms galaxies, but space between galaxies grows. This is not accidental. It is the outcome of gravity and expansion shaping the same universe in opposite ways. Gravity gathers, expansion separates. Light forms where matter concentrates. Darkness remains where space wins. That is a powerful way to understand the cosmic web. It is a map of a long contest. In galaxies, gravity has created order. In voids, expansion has preserved emptiness. The stars shine where the universe became dense enough to burn. The darkness remains where it did not. And this leads to another uncomfortable fact. Most of the matter in the universe does not shine at all. The stars, gas clouds, planets, and dust we can see are made of ordinary matter, the kind made from atoms. But ordinary matter is only a small fraction of the total cosmic energy budget. A much larger amount appears to be dark matter. Dark matter does not emit, absorb, or reflect light in the way ordinary matter does. We infer it through gravity. Galaxies rotate too quickly for their visible matter alone to hold them together. Galaxy clusters bend light through gravitational lensing more strongly than their visible matter can explain. The cosmic microwave background and large-scale structure point to a universe where unseen mass plays a major role. Dark matter helped shape the cosmic web. It provided gravitational scaffolding around which ordinary matter could gather. Without it, galaxies might have formed differently or far less efficiently. But dark matter itself remains invisible. It may be everywhere around galaxies, forming vast halos far larger than the visible stars. The Milky Way is not just the bright disk we see in images. It is embedded in an enormous halo of dark matter that extends far beyond the visible galaxy. This means the universe is dark not only because light has limits, it is also dark because much of what exists does not produce light. There is mass without glow, structure without shine, gravity without a visible surface. That idea changes the emotional meaning of darkness. The blackness of space is not proof that nothing is there. Sometimes it is proof that something is there in a form we cannot see directly. A dark matter halo may surround a galaxy. A cold cloud may hide future stars. A black hole may sit invisible until matter falls toward it. A planet may drift between stars without reflecting enough light to be detected. A dead star may cool silently over billions of years. Cosmic darkness is full of possibilities, but not all of them are comforting. It means the visible universe is only the illuminated edge of a much larger physical reality. And then there is dark energy. We will come to it more deeply in the second half of this journey, because it changes the future of darkness. For now, it is enough to know that the expansion of the universe is not merely continuing. On the largest scales, it is accelerating. Distant galaxies are being carried away from us faster and faster by the expansion of space. Over immense timescales, more and more galaxies will pass beyond our cosmic horizon. Their light will become more redshifted, dimmer, and eventually unreachable. The darkness is not only explained by the past, it is growing into the future. But before we look ahead, we need to understand something subtle about the present. The universe is not dark because there is not enough light. There is an extraordinary amount of light in the cosmos. Stars pour energy into space. Galaxies glow across billions of light years. Quasars outshine entire galaxies. Supernovae can become visible from immense distances. Gamma-ray bursts release staggering energy in brief moments. The cosmic microwave background fills all directions. Infrared light comes from dust warmed by stars. Radio waves arrive from gas, magnetic fields, pulsars, and active galaxies. The universe is alive with radiation. The problem is that light thins out, changes form, arrives late, misses us, or comes from objects too faint and distant for our eyes. The darkness is the result of filtering. Distance filters light. Time filters light. Expansion filters light. Matter filters light. Human vision filters light. A sky that looks black is not necessarily silent to a telescope. When astronomers point instruments into apparently empty patches of sky, they often find faint galaxies hiding there. The Hubble Deep Field was made by staring into a tiny, dark region of the sky that looked almost empty. The result revealed thousands of galaxies. A patch of darkness small enough to cover with a grain of sand held a deep crowd of ancient light. Later, deep fields went even farther. The James Webb Space Telescope has pushed into infrared wavelengths, revealing galaxies whose visible light has been stretched by expansion. What looked dark to older eyes becomes populated when seen with different instruments. This shows something important. Darkness is partly a limitation of exposure. If you look briefly, you see black. If you gather light for hours, days, or weeks, hidden galaxies appear. But even deep telescopes have limits. There are distances beyond which light is too faint, too redshifted, too ancient, or blocked by the early state of the universe. No telescope can see ordinary light from before the universe became transparent. No optical instrument can show us stars from a time before stars existed. Even perfect technology would face horizons built into cosmology. That is why the universe is dark in a more fundamental sense. Better instruments reveal more, but they do not reveal everything. They push back darkness. They do not erase it. Think about how strange that is. A dark patch of sky can contain galaxies. A deeper dark patch can contain older galaxies. Behind them can be light stretched into infrared. Behind that lies the cosmic microwave background. Behind that, from the viewpoint of light, there is no visible surface to observe because the universe was opaque. Darkness is layered. It is not one wall. It is a sequence of limits. Some limits are practical. Some are biological. Some are technological. Some are physical. The terrifying part is that physical limits do not care how advanced a civilization becomes. A civilization can build better telescopes, place observatories above its atmosphere, spread across star systems, or use gravitational lensing around stars to magnify distant light. But it cannot make light arrive from beyond its causal reach. It cannot observe a time before photons could travel freely. It cannot stop the expansion of space from stretching distant light. It cannot turn dark matter into something that shines just because seeing it would be easier. The darkness is not just a problem waiting for a clever solution. Some of it is permanent. Now, let us return to the simple experience of standing under the night sky. From Earth, most people see far fewer stars than humans saw thousands of years ago. City lights brighten the atmosphere. Air pollution and haze scatter artificial glow. Satellites cross long exposures. The modern sky can be dimmed not because the universe has changed, but because our planet has. That is a human-made darkness of another kind. Not the darkness of space, but the loss of our access to real darkness. In a bright city, only the moon, a few planets, and the strongest stars may remain visible. The Milky Way disappears. The faint structure of the night is erased by light from the ground. This is almost ironic. Artificial light hides cosmic light. We make the sky brighter and see less of the universe. But if you escape to a dark place, the stars return. You can see the Milky Way. You can see clusters and nebulae. You can watch meteors. You can feel how much is normally hidden. And yet, even in the darkest desert, even from the clearest mountain, even under the best natural sky on Earth, space remains mostly black. Human light pollution is not the deepest answer. It is a local veil. Remove it, and the cosmic question remains: why is the background still dark? Why do the stars not fill every gap? Why does the Milky Way look like a band rather than a sky-wide flame? Why do galaxies appear as faint islands rather than an ocean of brightness? Those questions lead us back to the same cosmic facts. The universe is young compared with infinite time. It is expanding. Light stretches, matter clusters, most space is empty, most matter is dark, and the visible universe is bounded by horizons. One reason this feels terrifying is that darkness reveals separation. The universe is not arranged for contact. Stars are separated by years of light. Galaxies are separated by millions of years of light. Clusters are separated by larger voids. The beautiful images we see from telescopes can make the universe feel crowded. They gather distant light into frames, brighten faint details, and compress huge scales into pictures our minds can handle. But if you were traveling through space, the dominant experience would not be colorful nebulae. It would be duration, silence, distance, blackness. A nebula that looks dense in a photograph is still a near vacuum by earthly standards. A galaxy that looks bright from far away contains more emptiness than matter. A star cluster that looks crowded still has enormous distances between its stars. The universe is visually magnificent because telescopes collect light patiently. The universe is physically lonely because its spaces are vast. This is why darkness is a more honest background than brightness. Brightness happens in special places. Darkness is the default. That default shapes everything. It shapes the temperature of space. It shapes how planets lose heat. It shapes how spacecraft survive. It shapes how stars appear from far away. It shapes how life experiences the cosmos from a small world with an atmosphere. If the universe were filled with thick, glowing gas, no planet like Earth could have the kind of night we know. If every direction were blazing, the temperature of space would be different. The history of life would be different. Our biology would be different. Perhaps the very possibility of calm night, circadian rhythms, astronomy, and looking outward depends on the universe being dark enough to reveal individual stars. There is beauty in that, but there is also a warning. The same darkness that makes the stars visible also shows how rare bright places are. Earth is not floating in a warm, luminous ocean. It is orbiting one star inside a thin atmosphere, surrounded by vacuum, protected by magnetic fields, chemistry, gravity, and distance. Change any of those conditions, and the darkness stops being peaceful. It becomes exposure. A human body in space does not meet a gentle black sky. It meets vacuum, radiation, extreme temperature differences, and no air. A spacecraft in deep space is not sailing through a glowing medium. It is moving through a nearly empty environment where every watt of heat, every bit of shielding, and every signal matters. The night sky is calm because we look at it from safety. The darkness itself is not safe. That is why the topic of cosmic darkness belongs on this channel. It is quiet enough to sleep to, but large enough to unsettle the mind. It begins with a simple question that anyone can ask. Why is space dark? And it opens into the deepest structure of reality, the beginning of time, the speed of light, the expansion of space, the birth of stars, the formation of galaxies, the limits of vision, the hidden mass of dark matter, the future influence of dark energy. A single black sky contains all of those answers. Now, let us explore one piece more carefully, the speed of light. Because light speed is not just a number, it is the rule that turns distance into history. When you look at the moon, you see it about 1.3 seconds in the past. When you look at the sun, you see it about 8 minutes in the past. If the sun vanished instantly, which it cannot do in any ordinary way, Earth would not know for about 8 minutes. The light would keep arriving. Gravity's change would also propagate at the speed of light. The solar system would continue behaving as if the sun were still there until information of the change reached it. For nearby stars, the delay is years. For nebulae, thousands of years. For nearby galaxies, millions. For deep galaxies, billions. Astronomy is therefore a form of time travel, but only in one direction. We look backward. We never see the distant universe as it is now. We see a stack of old messages arriving at different delays. That is why darkness can mean several things. It can mean no object is there. It can mean an object exists but is too faint. It can mean light has not arrived yet. It can mean light arrived in a wavelength we cannot see. It can mean the object has moved beyond the horizon. Or it can mean the universe at that time had not yet made the kind of light we are looking for. A black sky is not a simple answer. It is a question mark repeated in every direction. The observable universe is the region from which light has had time to reach us since the early universe became transparent. Its radius is often described as about 46 billion light-years in terms of current distance, even though the universe is only about 13.8 billion years old. That sounds contradictory. Until expansion is included, the light from the most distant observable regions traveled for almost the age of the universe, but while it traveled, space expanded. The place that emitted that light is now much farther away than the light travel time alone would suggest. This is another reason cosmic darkness feels strange. Distance in an expanding universe is not a simple ruler. A galaxy can send light when it was much closer, and by the time that light reaches us, the galaxy's present location can be far beyond where a naive calculation would place it. Some of the objects we observe today have already crossed into regions from which light emitted now will never reach us. We see their past, but not their future. They are visible and unreachable at the same time. This is one of the most haunting ideas in cosmology. The sky contains galaxies whose ancient light still arrives, even though their current story is already lost to us. We are looking at places that may no longer be communicable in principle. They are part of our observable past, but not our reachable future. The universe is dark for a reason. And one reason is that cosmic visibility is temporary. Light can arrive for a while, then expansion can carry the source beyond future contact. A galaxy does not have to disappear from existence to disappear from our future sky. It only has to recede beyond the ability of new light to bridge the growing distance. The blackness between galaxies is therefore not just empty background. It is a preview of separation. In the far future, if dark energy continues behaving as it does now, distant galaxies will fade from view. Local groups of galaxies may merge into isolated islands. Future astronomers, if any exist, might look out and see a much emptier universe than we see. The evidence for the Big Bang could become harder to find. The cosmic microwave background would be stretched to longer wavelengths, colder and weaker. The larger cosmic web could slip beyond observable reach. A civilization born too late might think its local galaxy island is all that exists. Darkness would hide the history we are currently lucky enough to read, but that belongs more fully to the second half. For now, the important point is this: darkness is dynamic. It has a past, it has a present, it has a future. The darkness after recombination was different from the darkness between galaxies today. The darkness inside a cosmic void is different from the darkness caused by redshift. The darkness of dark matter is different from the darkness of a starless region. The darkness of the far future will be different again. Using one word for all of it is convenient, but it hides the complexity. So let us name some of its forms. There is optical darkness, where visible light is absent or too weak for the eye. There is observational darkness, where light exists but lies outside our instruments or exposure limits. There is cosmological darkness, where expansion and horizons prevent information from reaching us. There is material darkness, where matter exists but does not emit light. There is historical darkness, where the universe had not yet formed stars. There is future darkness, where light sources will fade or be carried away. When we say the universe is dark for a reason, we are speaking about all of these at once, and they all point to the same conclusion. The universe is not built as a fully visible place. Visibility is partial. Light is local. Knowledge arrives delayed. Most of reality must be inferred from clues. That is why astronomy is so powerful. It does not simply collect beautiful images. It turns limited light into knowledge about things that are mostly hidden. A spectrum can reveal what a star is made of. A redshift can reveal how fast space has expanded since light was emitted. A gravitational lens can reveal unseen mass-bending light. A tiny fluctuation in the cosmic microwave background can reveal the seeds of galaxy formation. A dimming star can reveal a planet passing in front of it. A wobble can reveal an unseen companion. A pulse can reveal a neutron star. An accretion disk can reveal a black hole. We live in darkness, but the darkness leaves fingerprints. Still, the fingerprints are not the same as full sight. Every measurement is indirect compared with standing next to the thing itself. We know black holes exist not because we can see the black hole, but because we see matter and light behaving around it. We know dark matter exists because of gravity, not because it shines. We know the early universe through the afterglow it left behind, not by visiting it. We know distant galaxies by ancient photons, not by seeing their present. Our cosmic knowledge is both magnificent and incomplete. That incompleteness is built into the sky. Now, imagine the opposite universe. Imagine an eternal static cosmos filled evenly with stars, where every direction is bright. There would be no deep night, no black gaps, no isolated constellations. The sky would be a continuous furnace. Such a universe might be visually bright, but it would erase the clues that tell us our real history. The darkness is what lets us notice that the universe is expanding. It is what makes Olbers' paradox meaningful. It is what reveals that there was a beginning. It is what allows us to see galaxies as separate structures rather than a blended blaze. It is what makes the cosmic microwave background stand out as a faint relic. It is what gives astronomy depth. A perfectly bright sky would blind us in another way. The darkness is terrifying because it hides. But it is also useful because it separates. It creates contrast. A star is visible because the background is dark. A galaxy is outlined because the surrounding sky is dim. The Milky Way appears as a band because other directions are less crowded with visible stars and dust. The darkness is the canvas on which cosmic structure can be seen. But do not mistake the canvas for emptiness. The black regions in telescope images are often not blank. They may contain faint galaxies below the detection limit. They may contain diffuse gas. They may contain dark matter. They may contain cosmic rays. They may contain neutrinos passing through almost everything. They may contain gravitational waves stretching space by tiny amounts. They may contain radiation too cold or too red for our eyes. A visually dark universe is not a simple universe. It is a universe where most forms of presence do not resemble a lamp. This is why the search for darkness has become one of the central tasks of modern astronomy. We map the cosmic microwave background to study ancient light we cannot see directly. We map dark matter through gravitational lensing. We study the infrared universe to uncover galaxies hidden by dust or redshift. We use radio telescopes to search for hydrogen from the early universe. We observe supernovae to measure cosmic acceleration. We build detectors for particles that barely interact. We listen for gravitational waves from collisions invisible in ordinary light. Each new tool expands the meaning of seeing. Human vision ended at the eye. Astronomy continued by inventing new senses. Yet the more senses we build, the more we discover that darkness was not a lack of reality. It was a lack of access. And access is always limited. That is where the fear returns. Because if every improvement reveals more hidden structure, then the visible world is not the main world. It is the bright edge. The rest must be reached by inference, patience, and instruments that translate the universe into forms we can understand. When you look up tonight and see black space between the stars, you are looking at the boundary between direct experience and cosmic truth. Your eyes report darkness. Physics reports history. The two are not enemies. They are different levels of the same scene. The darkness is what the universe looks like to a small creature with limited senses. The hidden radiation, matter, and structure are what the universe becomes when that creature learns how to measure. Now consider dust. Dust sounds ordinary, almost dirty, but cosmic dust is one of the quiet sculptors of the visible universe. Tiny grains of carbon, silicates, and ice float between stars. They are much smaller than sand, yet across a galaxy they can change what we see. Dust can block visible light from stars behind it. It can turn a bright region into a dark lane. It can make the center of the Milky Way difficult to observe in ordinary light. When you see a dark band crossing the Milky Way in a good night sky, part of that darkness comes from dust clouds inside our own galaxy. They are not empty gaps. They are foreground material hiding the glow behind them. In visible light, dust is a curtain. In infrared light, it becomes less opaque. This is why infrared astronomy is so important. Infrared telescopes can peer through dusty regions and reveal newborn stars inside clouds that look black to optical telescopes. A dark nebula may be a nursery. A black patch may be a place where gravity is preparing future suns. That is another reason the universe is dark, for a reason. Some darkness is not caused by absence, but by birth. Stars often form inside cold molecular clouds, and those clouds can hide the process until the new stars become powerful enough to carve their way out. The universe does not always show creation while it is happening. It often hides it in cold gas and dust. This makes darkness feel different again. Not every dark place is dead. Some dark places are unfinished. Inside molecular clouds, temperatures can be only a few tens of degrees above absolute zero. Atoms and molecules move slowly. Gas is shielded from strong starlight. Gravity works quietly, gathering material into denser cores. Over time, a core may collapse. The center heats. A protostar forms. Jets may burst outward. A disk appears around the young star, and inside that disk planets may begin as dust grains collide and stick. From the outside, the region may look like a black shape against a brighter background. From the inside, it may be the beginning of a solar system. So darkness can be a womb. It can be a grave. It can be a horizon. It can be a limitation. It can be a sign of hidden mass. The same color in the sky can mean completely different physical things. This is why a slow journey through cosmic darkness cannot be only one explanation. If we reduced the answer to a simple sentence, we would lose the real terror. The dark universe is not a single mystery. It is many mysteries overlapping. One dark patch may be a nearby dust cloud. Another may be an intergalactic void. Another may be too faint for our exposure. Another may be ancient light shifted beyond visible wavelengths. Another may be a region beyond the reach of any signal. Another may contain dark matter that will never shine in the ordinary way. Another may simply be empty space, and even that emptiness has meaning. The universe is not dark by accident. It is dark through history, scale, composition, and fate. Now, think about black holes. A black hole is perhaps the most famous symbol of darkness. But even here, the idea is not simple. The black hole itself is dark because within the event horizon, no light can escape. But the region around a black hole can be among the brightest places in the universe. Matter falling toward a black hole forms an accretion disk, heating through friction and gravity until it glows across the electromagnetic spectrum. Jets can blast from near supermassive black holes and stretch for thousands of light years. Quasars can outshine all the stars in their host galaxies. The darkest object can create the brightest surroundings. This contradiction tells us something important. Darkness in space often marks a boundary. At a black hole, it is the boundary between what can send information outward and what cannot. At the cosmic horizon, it is the boundary between what can ever be observed and what cannot. At recombination, it is the boundary between an opaque universe and a transparent one. At a dust cloud, it is the boundary between visible light and blocked light. At the limit of the human eye, it is the boundary between biology and the broader spectrum. The universe is full of edges, and many of them look dark. A black hole may be surrounded by light, but the center remains an absence in the language of photons. The cosmic microwave background may fill the sky, but to human sight, it is hidden behind wavelength. A galaxy may be bright, but its halo may be dominated by unseen matter. The visible and invisible are tangled together everywhere. This is what makes the subject terrifying. Not that space is simply black, but that blackness can mean so many things we cannot directly enter. When early astronomers saw the night sky, they saw stars and darkness. They did not know that the darkness contained galaxies too faint for their eyes. They did not know that the Milky Way was one galaxy among many. They did not know that the universe was expanding. They did not know that invisible radiation from the early cosmos filled the sky. They did not know that most matter might be non-luminous. They did not know that the light of distant galaxies could be stretched by space itself. The darkness was already telling the truth. Humanity simply had not learned how to read it. Every generation of astronomy has turned a little more darkness into information. The telescope revealed fainter stars. Photography revealed nebulae and galaxies. Spectroscopy revealed chemical elements and motion. Radio astronomy revealed invisible gas and cosmic background radiation. Infrared observatories revealed hidden star formation and red-shifted galaxies. X-ray telescopes revealed hot gas, neutron stars, and black hole environments. Gravitational wave detectors revealed space-time ringing from compact collisions. The pattern is clear. Whenever we build a new way to look, darkness loses one disguise and keeps another. That is why the universe remains mysterious even after so much discovery. Science does not make the cosmos smaller. It makes the unknown more specific. Instead of asking, "Why is the sky dark?" we now ask which darkness we mean. Is it darkness from finite age, from cosmic expansion, from dust, from voids, from dark matter, from human eyesight, from horizons, from the future? The answer depends on the scale, and that is why the universe is dark for a reason, not for one reason. It is a layered darkness produced by the deepest laws we know. If this first half of the journey has done its work, the night sky should no longer feel like simple emptiness. It should feel like a map of limits, a record of light that arrived, a silence from places too far away, a cooled echo from the early universe, a sign of matter that refuses to shine, a reminder that the cosmos was once starless, a background against which every sun becomes visible. The second half will take this farther, because the darkness we see today is not the final state. The universe is still changing. Galaxies continue to drift apart. The cosmic microwave background continues to cool. Stars continue to burn through their fuel. Gas supplies are slowly being consumed. The expansion of space continues to reshape what can ever be seen. And dark energy may be preparing a future in which the universe becomes more isolated, more silent, and more difficult to understand. The darkness above us is already ancient, but it is also unfinished. It began before the first stars. It surrounds us now between the galaxies, and it may eventually become the dominant story of everything. So in the next part, we leave the darkness of the past and present behind and follow the universe toward the deeper darkness waiting in its future. That future darkness does not arrive all at once. It does not fall over the universe like a curtain. It does not switch off the galaxies in a single instant. It begins quietly, in the same way most cosmic changes begin, with distances becoming larger, energies becoming thinner, and light losing a little more of itself while crossing space. If you could step outside the Milky Way and watch the universe for billions of years, you would not see darkness racing toward you like a storm. You would see something slower and stranger. Galaxy clusters would keep their shapes for a while. Spiral galaxies would keep turning. Red stars would keep glowing. Black holes would keep feeding when matter wandered too close. New stars would still form inside cold clouds, but not as often as before. The night would remain filled with points of light. A civilization living during that age might not feel that anything terrible was happening. Their skies would still have constellations. Their telescopes would still find nebulae. Their astronomers would still measure galaxies and supernovae, and the ancient glow of the cosmic microwave background. But underneath that ordinary-looking universe, a deeper change would already be underway. The universe would be using up the easy fuel. Stars are not made out of nothing. They are built from clouds of cold gas, mostly hydrogen, with smaller amounts of helium and heavier elements mixed through the darkness. When gravity gathers enough of that gas into dense regions, pressure rises, temperature climbs, and eventually the center of a cloud becomes hot enough to ignite nuclear fusion. That is the birth of a star. For most of cosmic history, this process has made the universe visible. Stars turn hidden gas into light. They take matter that cannot be seen easily and make it shine across millions or billions of years. But every star is also a way of locking fuel away. Some of the gas becomes part of the star itself. Some of it is blown back into space by radiation, winds, and explosions. Some of it is heated until it can no longer collapse easily. Some of it is pulled into black holes. Some of it is trapped in stellar remnants, planets, asteroids, and dead systems. So, star formation is not a machine that can run forever at the same speed. It depends on a supply chain. It needs cold gas. It needs gravity to collect that gas. It needs regions dense enough to overcome pressure, turbulence, magnetic fields, and heating from older stars. Over time, galaxies change because the raw material changes. Young galaxies were often messy, gas-rich, and violent. They collided more often. They fed on streams from the cosmic web. They built stars rapidly, sometimes in enormous bursts. The early universe was not brighter to human eyes because it was far away and redshifted and full of limits. But it was far more active in the creation of new stars. Our era is already calmer. The Milky Way still forms stars, but it is not in its wild youth. Many giant elliptical galaxies have almost stopped forming stars entirely. They glow with old populations of red and yellow stars, like cities where almost no new children are being born. They are not dead in the sense of being invisible. They can remain bright for a long time, but their brightness is inherited. It comes from older generations. The future of such galaxies is not explosive creation, but slow fading. This is one reason the universe is dark, for a reason. Darkness is what remains when the universe is no longer converting enough cold gas into new fire. It is not only emptiness, it is exhaustion. It is the fading result of a finite supply of fuel inside an expanding cosmos. And because the expansion continues, the problem grows deeper. Imagine two galaxies separated by a vast region of space. They are not flying away from each other through space like rockets. The space between them is stretching. As that stretching continues, the light traveling across it is stretched as well. Blue light becomes redder. Visible light becomes infrared. Infrared becomes microwave. Microwave radiation becomes longer and colder. The farther the light travels, and the more the universe expands while it travels, the more that light is drained of its original energy. This is not because the photons become tired in the ordinary sense. It is because their wavelength grows with the geometry of the universe itself. The same expansion that creates distance also changes the message carried by light. So the darkness of the far universe is not simply the absence of sources, it is also the weakening of signals. A galaxy can shine powerfully in its own time, but by the time its light reaches us, that light can be stretched into wavelengths our eyes cannot see. With optical vision alone, the early universe would seem far darker than it really was. With infrared telescopes, some of that hidden light returns. With radio telescopes, other ancient signals become accessible. Every improvement in astronomy teaches the same lesson. Darkness often means our senses are tuned to the wrong part of the spectrum. A wall of black invisible light may be glowing in infrared. A blank patch between galaxies may contain weak radio emission. A cold cloud may be invisible to the eye, but detectable by molecules whispering at specific wavelengths. A galaxy hidden by dust may reveal itself through the warmth of that dust. But even this has limits. Technology can widen the window, but it cannot remove the horizon. There are regions from which light emitted today will never reach us, not because our telescopes are weak, but because the expansion of the universe is carrying those regions away too quickly for their new light to cross. The growing distance, that is a different kind of darkness. It is not darkness from ignorance. It is darkness from causal separation. There are places that may continue to exist, places with galaxies and stars and planets, and perhaps even life. But their future signals are already beyond our reach. If someone there turns on a beacon tonight, the beam may never arrive here. If a star explodes there tomorrow, the flash may remain forever outside our observable future. The universe does not need to destroy something to hide it. It only needs to expand space fast enough. This is one of the most unsettling ideas in modern cosmology. The observable universe is not the whole universe. It is the part from which light has had time to reach us since the beginning of cosmic history. And as the expansion accelerates, the boundary of what can influence us becomes more severe. The universe is not only dark because the sky contains empty gaps. It is dark because reality is divided into regions that can no longer exchange information. A telescope is a time machine, but only inside the part of time and space connected to us. Beyond that, the universe may as well be sealed. This does not mean the cosmic horizon is a physical wall. A spacecraft would not crash into it. There is no glowing line in the dark where the accessible universe ends. The horizon is a relationship between distance, time, light speed, and expansion. It is the limit of communication. It is the boundary of what can ever become part of our story. And that boundary gives darkness a new meaning. When we look into the night, we are not only seeing objects, we are also seeing the absence of unreachable futures. The blackness between distant galaxies is partly a record of what cannot speak to us anymore. Dark energy makes this more dramatic. We use the term dark energy because we do not fully understand what is driving the accelerated expansion of the universe. It is not dark like a shadow. It is dark because it is unknown, invisible directly, and detected through what it does to cosmic expansion. Its effect is not local in the ordinary sense. Dark energy does not rip a table apart. It does not tear the moon away from Earth today. Gravity still holds galaxies together. Electromagnetism still holds atoms together. The solar system remains bound. The Milky Way remains bound. The local group remains gravitationally connected. But on the larger scales, where galaxies are separated by enormous distances and not tied together strongly enough by gravity, the expansion wins. Over very long times, more and more distant galaxies will slip beyond visibility. Their light will become more redshifted. Their apparent motion away from us will increase. Their signals will fade into wavelengths so long and so weak that future observers may not detect them at all. A sky that now contains billions of galaxies will become emptier. Not because all those galaxies vanish from existence, because the connection is lost. Imagine a future astronomer living inside the merged remnant of the Milky Way and Andromeda. By then, our two large galaxies will have become one enormous system, often called Milkomeda in informal descriptions. The collision will not look like two solid objects smashing, because galaxies are mostly empty space. Stars are separated by such great distances that direct stellar collisions will be rare. But gravity will reshape the entire structure. Spiral arms will be torn apart. Streams of stars will arc through space. Gas clouds will collide and ignite waves of star formation. The supermassive black holes at the centers may eventually merge. For a while, the local sky could become spectacular. But beyond that merged island, the rest of the universe will be drifting away. If dark energy continues behaving as it appears to behave today, distant galaxies will disappear from the observable sky. After enough time, future astronomers inside that local island might see only their own galaxy and its bound companions. The cosmic microwave background would be stretched to enormous wavelengths, cooled far below its already faint temperature. The evidence of the Big Bang would become almost impossible to detect. The expansion of the universe itself might be much harder to infer. From their point of view, the cosmos could look like a lonely island of stars, surrounded by apparently eternal darkness. That is terrifying in a very quiet way. It means the universe is not equally understandable at every time. We live during an era when evidence is still available. The cosmic microwave background can still be measured. Distant galaxies still fill deep images. Supernovae can still reveal accelerated expansion. Large-scale structure can still be mapped. Ancient light still carries information from early epochs. But those clues are not guaranteed forever. The universe is not just becoming darker physically. It may also become harder to interpret. Cosmology has an expiration date for some observers. The darkness of the future could hide the origin of everything from anyone born too late to receive the evidence. This is one of the reasons the present era is precious. Not because it is the center of the universe, not because humans occupy a special cosmic throne, but because we exist during a window when the sky still contains enough information to reconstruct an enormous story. We can see galaxies at many stages of development. We can detect the afterglow of the early universe. We can measure expansion. We can compare nearby young stars with distant ancient galaxies. We can watch the universe not as a single still image, but as a layered archive. That archive is written in light. And because light can be delayed, stretched, absorbed, scattered, and lost beyond horizons, the archive is fragile. The darkness is not empty paper. It is paper where some ink has never arrived. Some ink has faded into invisible colors, and some pages are moving forever out of reach. Now, step from the largest scales back down to the galaxies themselves. Inside them, darkness has another source. Stars do not illuminate all space evenly. Even in a bright galaxy, most of the volume is still dark. The Milky Way contains hundreds of billions of stars, but if you could travel between them, you would spend almost all of your journey in blackness. A star is enormous compared with a planet, but tiny compared with interstellar distances. The Sun is about 1.39 million kilometers wide. The nearest other star system is more than 4 light-years away. Between here and there is not a glowing corridor. There is sparse gas, dust, cosmic rays, magnetic fields, small icy bodies, and an immense amount of night. The stars make the galaxy visible from afar, but they do not fill it with daylight. This is why even a universe rich with stars can still be dark. Brightness is not only about how many lights exist, it is about how far apart they are. A city seen from an airplane may look like a carpet of light, but between the lamps there are streets, rooftops, alleys, and shadows. Now, increase the scale until each lamp is a star, and each gap is measured in trillions of kilometers. The darkness stops being surprising. It becomes the natural background. The same logic applies between galaxies with even greater force. A galaxy can contain 100 billion stars and still be separated from the next large galaxy by millions of light-years. Galaxy clusters contain many galaxies, but between clusters are vast voids. The cosmic web has filaments, knots, sheets, and empty-looking regions. Matter is not spread like fog through all space. It is arranged in structure, and structure requires contrast. If everything were bright everywhere, the universe would have no visible shape. Darkness is what reveals the pattern. The night between stars allows constellations to exist. The voids between galaxies define the cosmic web. The black background of space makes a nebula visible. A universe without darkness would not be more beautiful to us. It would be unreadable. That may sound peaceful, but the reason behind it is not poetic. It comes from gravity and expansion fighting across time. Gravity pulls matter together. Expansion increases distances on large scales. Dark matter deepens gravitational wells. Gas falls into those wells, heats, cools, collapses, and sometimes forms stars. Radiation from stars heats surrounding gas and prevents other stars from forming too quickly. Supernovae blow material outward. Black holes inject energy into galaxies and clusters. The result is not uniform light. It is a universe with bright knots and dark spaces. Cosmic darkness is therefore not a failure of creation. It is part of the architecture. Without the dark gaps, the bright structures could not stand out. Without empty regions, galaxies would not be islands. Without the cooling of the universe, atoms would not have formed. Without the early dark ages, the first stars would not have had a neutral hydrogen universe to ignite. Darkness is not just what came before light. It is what gives light a place to happen. But there is another kind of darkness that feels less like structure and more like disappearance. This is the darkness created when stars age. Every star begins as a balance between gravity and pressure. Gravity tries to crush the star inward. Fusion in the core produces energy and pressure that pushes outward for millions, billions, or even trillions of years, depending on the star's mass. This balance can remain stable. But fuel changes. Hydrogen becomes helium. In heavier stars, helium becomes carbon-oxygen, and heavier elements through different stages of fusion. Massive stars burn quickly and die violently. Small red dwarfs burn slowly and may outlive almost everything else. Yet no ordinary star shines forever. The universe is dark in the future because every light source has a lifetime. The most massive stars are like fireworks. They burn intensely, forge heavy elements, and end in supernovae or collapse into black holes. They help enrich the universe, but they do not last long. Stars like the Sun live longer, then swell into red giants, shed outer layers, and leave white dwarfs behind. The smallest stars can remain stable for astonishing spans of time, slowly converting hydrogen into helium with extreme efficiency. They will be the last long-lived stellar lamps. For ages far beyond the current age of the universe, red dwarfs will continue glowing. If any planets around them remain stable and habitable, they may become the late campfires of cosmic history. But even they are not eternal. Eventually their fuel will be exhausted. They will cool into compact remnants. The era of new starlight will end. When that happens, the darkness of the universe will no longer be mainly the darkness between stars. It will be the darkness after stars. This is difficult to imagine because every human experience of night depends on a universe that still has abundant light. Even when you stand under a dark sky, the darkness is surrounded by active stars. The Milky Way glows. Distant galaxies shine. The sun will rise again. The darkness is temporary from a human point of view. But cosmic time changes that comfort. There will be an age when no new stars are being born in the ordinary way. There will be an age when galaxies are filled mostly with remnants. White dwarfs, neutron stars, black holes, cold planets, rogue worlds, dark matter halos, dust that no longer catches much light. The universe will still contain objects, but objects do not guarantee illumination. A galaxy of dead stars is not gone. It is simply no longer a lantern. White dwarfs will cool slowly. At first, they remain hot enough to glow. They are the exposed cores of stars like the Sun, dense and Earth-sized, holding much of a star's mass in a tiny volume. They shine with leftover heat rather than ongoing fusion. Over enormous timescales, they radiate that heat away. They become dimmer. They shift from white to red, to infrared, to something colder and darker. Eventually, in a future so distant that the current universe has not yet produced one, they may become black dwarfs. A black dwarf would be a cooled stellar remnant, no longer glowing visibly. It is a theoretical object because the universe is not old enough for white dwarfs to have cooled that far. That fact itself is a reminder of how young the universe still is. We talk about the end as if it is close, because the idea is emotionally powerful. But physically, the cosmos has almost all of its future still ahead of it. The darkness waiting in that future is not rushing toward us. It is unimaginably patient. Neutron stars will also cool. They are born in violence from the collapsed cores of massive stars. At birth, they can be incredibly hot, magnetic, and energetic. Some spin rapidly as pulsars, sweeping beams of radiation through space, like cosmic lighthouses. But pulsars slow down. Magnetic fields evolve. Heat leaks away. Neutron stars become quieter. They may remain detectable through gravity or rare interactions, but their active brightness fades. Black holes, meanwhile, are dark in a more literal and more complicated sense. A black hole is not simply a star that stopped shining. It is a region where gravity is so intense that inside the event horizon, escape paths lead inward. Light cannot leave once it crosses that boundary. Black holes can be surrounded by brilliant disks of superheated material. They can power quasars and jets. They can light up galaxies when they feed. But the black hole itself is defined by a darkness from which light does not return. In the long future, when gas supplies are scarce and stars are gone, many black holes will be quiet. They will not appear as glowing monsters. They will be almost invisible gravitational presences in an increasingly cold universe. Even black holes are not expected to last forever if Hawking radiation is correct. Quantum effects near the event horizon allow black holes to lose energy extremely slowly. For stellar mass black holes, the timescales are so enormous that they make stellar lifetimes look like sparks. For supermassive black holes, the times are almost beyond language. Still, the direction is important. In the far future, after stars have ended and remnants have cooled, black holes may become the last major engines changing the universe. Then, over absurdly long times, even they fade. That is when darkness becomes almost complete. Not the ordinary darkness of night. Not the beautiful darkness behind the stars. Not the ancient darkness before galaxies, but a thermal darkness, where almost all useful energy has been spread thinly across space. This is the idea behind heat death. The term can sound misleading because it does not mean the universe becomes hot. It means differences in usable energy disappear. Heat can do work when it flows from hot regions to cold regions. Stars shine because their cores are hotter than their surroundings. Planets have weather because energy moves through atmospheres and oceans. Life survives because energy gradients exist. When energy becomes too evenly spread, there is no organized flow left to power complex processes. In that sense, the universe does not die by exploding. It dies by losing contrast. No bright against dark. No hot against cold. No young stars against old space. No dense clouds collapsing into suns. Just thin, exhausted radiation and whatever stable particles remain. This is one possible future. Based on our current understanding, science must stay honest here. We do not know every detail of the ultimate fate of the universe. Dark energy may not behave exactly as a constant forever. Particle physics may contain surprises. Protons may or may not decay on timescales far beyond anything we can measure now. Black hole evaporation has strong theoretical foundations, but has not been observed directly for astrophysical black holes, because the effect is far too tiny today. Cosmology is powerful, but it is not complete. Still, the broad picture is unsettling enough. The universe is dark now for reasons we can explain. It may become darker later for reasons we can predict. The present sky is not the final sky. It is a temporary stage in the transformation of cosmic energy. And this brings us back to the most familiar question. Why is the night sky dark? At the beginning of this journey, the question sounded almost childish. Look up, and the answer seems obvious. The sky is dark because space is empty. But that answer fails almost immediately. Space is not perfectly empty. The universe contains trillions of stars and countless galaxies. If it were infinite, eternal, static, and evenly filled with stars, every line of sight should eventually end on a stellar surface. The sky should blaze. So the darkness tells us those assumptions are wrong. The universe has a finite observable age. Light has not had infinite time to arrive. Space is expanding. Light is redshifted. Stars have finite lifetimes. Matter is arranged in structures separated by voids. Much of the mass does not shine. Much of the energy driving expansion remains mysterious. Our eyes see only a narrow band. Our telescopes reveal more, but not everything. Horizons place hard limits on what information can reach us, and the future will remove some evidence that is visible now. The darkness above us is therefore not a simple background. It is a scientific statement. It says the universe began in a hot, dense state, expanded, cooled, formed atoms, waited through dark ages, ignited stars, built galaxies, created heavy elements, accelerated apart, and is still evolving toward a colder future. It says light is powerful, but not all-powerful. It says distance matters. It says time matters. It says even the most brilliant objects cannot erase the limits written into the cosmos. The terrifying part is not only that the universe is dark, it is that darkness reveals how little of the total reality can ever touch us. We can map billions of galaxies, but not all galaxies. We can detect the ancient microwave glow, but not what lies beyond the observable horizon. We can infer dark matter from gravity, but not hold it in our hands. We can measure dark energy from expansion, but not yet explain its nature. We can look backward almost to the beginning, but not through the earliest opaque fire. We can imagine the far future, but we cannot visit it. Every direction contains knowledge and a boundary. That combination is what makes the universe feel both understandable and unreachable. A completely unknowable universe would be only mystery. A completely transparent universe would be only mechanism. Our universe is neither. It gives us clues, then hides the rest behind time, distance, expansion, and physics. That is why astronomy can feel so strange. It is not just the study of what is bright. It is the study of what brightness fails to reveal. When a telescope takes a deep image of space, the image is not simply filled with galaxies. It is also filled with dark intervals between them. Those intervals are part of the result. They tell us where matter did not collect. They mark distances light has crossed. They frame the tiny islands where stars have formed. The black pixels are not mistakes. They are the room in which the universe built structure. When a radio telescope listens for the 21-centimeter signal from ancient hydrogen, it is not only looking for light, it is looking for the shape of darkness before the first stars fully transformed the gas between galaxies. When scientists map gravitational lensing, they are not only mapping visible matter, they are tracing dark matter through the way it bends background light. When cosmologists measure supernovae, they are not only watching stellar explosions, they are using those explosions to expose the expansion of space. Again and again, darkness becomes data, not because it stops being dark, but because we learn which kind of dark it is. That may be the calmest answer to the title of this video. The universe is dark for a reason, because darkness is not one thing. It is the combined result of cosmic history, human perception, finite light speed, expanding space, invisible matter, aging stars, and horizons that cannot be crossed by information. But there is also a more disturbing answer. The universe is dark for a reason, because it was never built to be fully visible from one place. No planet can stand at the center and see everything. No telescope can escape all horizons. No civilization can receive every signal. The cosmos does not arrange itself around observers. It gives each observer a bubble of accessible history and leaves the rest outside. From Earth, our bubble is enormous by human standards. It contains galaxies so distant that their light began traveling before the sun existed. It contains radiation released when the universe was only a tiny fraction of its current age. It contains evidence of forces and matter we still do not fully understand, but by cosmic standards, it is still only a bubble. The darkness beyond it is not empty just because we cannot see it. It is beyond the reach of the signals available to us. This matters because it changes what humility means. Humility is not simply saying we are small. That can become too easy, almost decorative. The deeper humility is recognizing that our entire view of existence is local. Not local like a city or a continent. Local on the scale of causality. We live inside a region where light has managed to arrive. We build science from signals that crossed our horizon in time. We call that picture the observable universe. But the name already contains the warning. Observable does not mean total. It means available. The darkness is the edge of availability. At the same time, that should not make the search feel pointless. Limits are not failures. They are the conditions under which knowledge becomes meaningful. A map with no borders would tell us little about where we stand. A sky with no darkness would hide the stars in uniform brightness. A universe with no distance would have no history written in light travel time. Because light takes time to move, looking outward means looking backward. Because the universe expands, distant galaxies carry the record of that expansion in their stretched light. Because the early universe cooled, the microwave background remains as a fossil signal. Because matter clumped, galaxies formed, and voids opened. Because some matter does not shine, gravity reveals what light cannot. The same rules that hide the universe also make it readable. That is the strange balance. Darkness blocks, but it also frames. It removes, but it also preserves contrast. It frightens, but it also tells the truth. If the sky were bright in every direction, we might never have discovered the expansion of the universe in the same way. We might never have asked why the background is not filled with stellar fire. The darkness forced the question. The question opened the door. Behind that door was modern cosmology. A hot beginning, a finite age, a changing space, an afterglow, dark matter, dark energy, cosmic horizons, a future of fading light. All of that was hidden inside one ordinary experience. You look up at night, and most of what you see is black. The ordinary mind moves past it. The scientific mind asks why, and the answer is almost the entire story of the universe. So when you think of space as dark, do not imagine it as empty nothingness. Imagine it as a layered record. Some layers are ancient, some are local, some are invisible to your eyes but bright to instruments. Some are made by the limits of time. Some are made by the expansion of space. Some are made by matter that has gravity but no light. Some are made by stars that have not yet formed. Some are made by stars that have already died. And some are waiting in the future when the universe grows colder and quieter than it is now. This is why the darkness is terrifying. Not because it means there is nothing there, because it means there is more than we can receive. The black sky is not a wall of emptiness. It is an ocean of limits, distances, vanished signals, hidden matter, cooled radiation, and unreachable futures. Every star you see is a temporary puncture in that darkness. Every galaxy is a distant island of fire, surrounded by expansion. Every photon that reaches your eye has won a race across space and time. Most photons that could have told other stories will never arrive. And yet, from the few that do arrive, we have learned astonishing things. We have learned that the universe had a beginning we can study. We have learned that stars are factories of elements. We have learned that galaxies grow from invisible scaffolding. We have learned that space itself changes. We have learned that the sky is dark because the universe is not eternal in the simple way people once imagined. We have learned that darkness is not the absence of explanation. It is the reason explanation was needed. There is also a practical side to this cosmic darkness, one that matters every time we build a new observatory. Astronomy is the art of separating faint signals from darker backgrounds. A distant galaxy is not only far away, it is spread across the sky. Its light can be smeared into a glow so faint that the galaxy is technically present in the image, but almost impossible to notice. This is called low surface brightness. A galaxy can contain many stars and still be difficult to see if its light is distributed over a wide area. So darkness is not always the result of absence. Sometimes it is the result of dilution. A bucket of paint looks bright when it is concentrated in one place. Spread the same paint across a field, and the color becomes weak. Light behaves differently from paint, but the idea helps. If a galaxy's starlight is thinly spread across a large patch of sky, each part of the detector receives very little light. The object becomes ghostly. It may require long exposure times, careful processing, and dark observing sites to reveal it. This means the universe may contain structures that are not hidden by walls, dust, or horizons, but by faintness. They are too spread out. They are too gentle against the noise. They live near the edge of what instruments can distinguish from background darkness. The same is true for the outskirts of galaxies. A bright spiral disk may be obvious, but its faint halo of stars extends much farther than the easy image suggests. Streams from ancient mergers may wrap around a galaxy like pale scars. Dwarf galaxies may drift nearby, barely glowing. Globular clusters may survive as old fragments of violent history. The visible galaxy is only the bright core of a larger gravitational story. Around it sits a dark matter halo, far more massive than the stars alone imply. We do not see that halo as light. We infer it from motion. Stars orbit too quickly. Gas behaves as though extra mass is present. Galaxies in clusters move as if bound by more matter than telescopes can directly observe. Light from background galaxies bends around invisible mass through gravitational lensing. Dark matter turns darkness into a kind of lens. It does not glow, but it shapes where glowing things appear. This changes the meaning of a dark patch of space. A region may look empty to the eye, while still containing mass that bends light, anchors galaxies, or guides the growth of structure. The universe can be dark and active at the same time. Invisible does not mean irrelevant. In fact, much of the visible universe may be visible only because invisible matter helped organize it. Without dark matter, galaxies might not have formed the way they did. The bright islands of stars could depend on a scaffold that never shines. That idea is unsettling because it reverses the normal instinct. We tend to think light reveals what matters. Cosmology says some of what matters most may reveal itself only indirectly. A dark ingredient can dominate the architecture of galaxies. An unseen energy can influence the expansion of space. A background glow too cold for our eyes can preserve evidence from the early universe. The deeper we look, the more often darkness becomes part of the machinery rather than just the absence of it. Even dust has this double role. Dust blocks visible light, turning parts of the Milky Way into dark lanes. For centuries, those lanes looked like holes in the stars. They were not holes. They were clouds of tiny grains absorbing and scattering light from stars behind them. In visible images, they look like wounds across the galaxy. In infrared images, many of those same regions open up. Stars behind the dust become visible. Newborn stars embedded inside dusty clouds reveal themselves through heat. A region that looks dark to one telescope becomes luminous to another. So the question is never only, is it dark? The better question is, dark to what? Dark to an optical telescope. Dark in ultraviolet, dark in infrared, dark in radio, dark gravitationally. Dark because the signal is absent, or because the receiver is wrong. A sleeping universe and a hidden universe can look similar until we change the instrument. This is why modern astronomy uses the entire electromagnetic spectrum. Visible light shows stars like the sun. Infrared light reveals warm dust, cool stars, and distant galaxies whose light has been stretched by expansion. Ultraviolet light reveals hot young stars and energetic processes. X-rays reveal superheated gas, neutron stars, black hole accretion disks, and violent environments. Gamma rays reveal some of the most extreme events in the cosmos. Radio waves reveal cold hydrogen, pulsars, molecular clouds, and relic radiation. Each wavelength turns one kind of darkness into information. But no wavelength turns the whole universe transparent. Every method has its own limits. Atmospheres absorb some radiation. Detectors have noise. Signals weaken with distance. Foreground sources interfere. Cosmic expansion shifts ancient light into different bands. Dust can glow and confuse the measurement of more distant objects. Gravity can magnify one galaxy while distorting its shape. Even the best map is filtered through physics. That filtering is not a mistake. It is the condition of observation. We never receive the universe directly. We receive messages processed by distance, time, matter, and expansion. The darkness is part of that processing. Consider the cosmic microwave background again. To human eyes, it is invisible. To a microwave instrument, it fills the entire sky. It is often called the afterglow of the Big Bang, but even that phrase can make it sound brighter and more dramatic than it appears today. Its temperature is only about 2.7 Kelvin. It is incredibly cold. It is almost uniform. The differences across the sky are tiny, measured in fractions of a degree. And yet, inside those tiny differences lies the seed pattern of cosmic structure. Slightly denser regions grew into larger structures over time. Slightly less dense regions became emptier. The early universe did not need dramatic shadows to create the darkness we see now. It needed small differences amplified by gravity over billions of years. This is another reason the universe is dark. The large-scale structure grew from subtle beginnings. A nearly smooth early cosmos became a web of bright filaments and dark voids. The darkness is not random. It has ancestry. It carries the memory of early density fluctuations stretched across cosmic time. When you look at deep images of galaxies, you are seeing the late result of those early patterns. When you look at voids, you are seeing regions where matter never collected enough to blaze with many galaxies. The cosmic web is not a decoration. It is the universe remembering its initial conditions through gravity. And that makes the black spaces between structures feel different. They are not simply where nothing happened. They are where less happened, where matter flowed away, where gravity built elsewhere. In a universe shaped by contrast, emptiness has a history too. There is also darkness caused by scale itself. Many things in the universe are bright, only if you are close enough. The sun is overwhelming from Earth. From far beyond the outer planets, it becomes a bright star. From another star system, it would be one point among many. From across the galaxy, it would vanish into the combined glow of the Milky Way. From another galaxy, it would be completely impossible to separate. Brightness is relational. A star that dominates one world may be invisible from another. The universe is dark partly because every light source loses its personal importance with distance. This can feel almost emotional, but it is simple physics. Light spreads out. A fixed amount of energy covers a larger and larger sphere as it travels. The intensity drops with distance. At cosmic scales, expansion stretches the light as well, reducing its energy further. A source may be real, powerful, and active, yet still contribute almost nothing to a distant observer. So darkness is also perspective. Not illusion, but perspective enforced by geometry. From Earth, the sun is life. From most of the universe, the sun is undetectable. That should make us cautious about judging the cosmos by what appears obvious from here. There may be countless local dramas that do not register across the vastness. Planets may form, oceans may freeze, civilizations may rise and vanish, stars may flare, small moons may hide chemistry beneath ice. To the wider universe, almost all of it is silent. The darkness is not proof that nothing is happening. It is proof that most happenings are local. This is especially important when thinking about life. A living planet would not necessarily be easy to see. Earth itself, from many light years away, would be a faint dot next to a bright star. Its atmosphere might reveal oxygen, water vapor, methane, or other clues if the observer had powerful enough instruments in the right position. But Earth would not announce itself across the galaxy as an obvious beacon. For most of cosmic history, life on Earth produced no radio signals, no city lights visible between stars, no spacecraft leaving the solar system. For billions of years, the only evidence was subtle chemistry on a small rocky world. That means the universe could be dark, even if it contains life. Life does not automatically fill space with visible signs. A biosphere can be real and quiet. An ocean under ice can be alive and hidden. A microbial world can alter chemistry without creating anything that looks like a message. So one of the most haunting possibilities is not that the darkness is empty. It is that it may contain things too small, too distant, too faint, or too unfamiliar for us to recognize. The silence of the night does not settle the question. It deepens it. This connects the darkness of cosmology to the silence of the search for extraterrestrial intelligence. The Fermi paradox is often summarized by the question, where is everybody? But perhaps part of the answer lies in the same logic that explains the dark sky. Signals are limited, distances are enormous, civilizations may be rare, brief, quiet, or not technological in ways we recognize. Radio waves spread and weaken. Beams may miss us. Time windows may not overlap. A galaxy can contain many worlds and still look dark to observers who do not know exactly where or how to search. Again, darkness does not mean nothing. It means connection is difficult. The universe may be filled with separations larger than intention. Even if someone wants to be found, the message still has to cross the dark. And the dark is patient. It can outlast almost any signal. There is one more layer that matters before we reach the ending. Human darkness is not the same as cosmic darkness. For most of human history, night was one of the main ways people experienced the universe. The Milky Way was visible to the naked eye. The stars were part of navigation, myth, agriculture, and memory. Today, many people live under artificial sky glow. Their night is brightened by cities, but their universe is hidden. This creates a strange inversion. We have more astronomical knowledge than any ancient civilization, but many people can see fewer stars with their own eyes. Our local darkness has been replaced by artificial light, while the true cosmic darkness becomes less familiar. That does not change the universe, but it changes our relationship to it. When the natural night disappears, the dark sky stops being a daily reminder of scale. The universe becomes something seen through screens, images, telescopes, and data. Those tools are powerful, but the emotional shock of looking up matters too. A truly dark sky teaches instantly what numbers struggle to express. It shows that Earth is surrounded by depth. It shows that light is rare enough to be counted. It shows that darkness is not an abstract concept, but the visible condition of the cosmos. Protecting dark skies is not only about astronomy. It is about preserving access to one of the oldest human experiences of reality. The irony is sharp. We brighten our cities and lose the universe. We escape local darkness and become blind to cosmic darkness. But the real night remains above the artificial glow, unchanged and waiting. Above the atmosphere, beyond satellites and clouds, the same vast blackness continues. It does not care whether we look. It does not become less deep because we hide it from ourselves. This is why the title of this video has more than one meaning. The universe is dark for a reason scientifically, because of age, expansion, redshift, matter distribution, invisible mass, and future evolution. But it is also dark for a reason emotionally, because darkness is the only background large enough to hold the scale of everything. If every part of the sky were bright, we might feel surrounded by presence. Instead, we are surrounded by distance. The stars are not the dominant thing in the sky. The dominant thing is the space between them. That space is where the lesson waits. It tells us that light is an event, not a guarantee. It tells us that every visible object is temporary. It tells us that the universe is not a room filled with lamps, but a history of fires separated by oceans of time. And once you understand that, the darkness no longer feels like a blank background. It feels like the main character. The stars are interruptions. The galaxies are temporary gatherings. The nebulae are brief clouds caught in transformation. The darkness is what came first, what remains between, and what may return more completely at the end. Even our own solar system teaches this lesson in miniature. From Earth, the sun feels like the obvious center of brightness. It warms oceans, drives weather, lights the moon, and makes daytime feel normal. But travel outward and the sun's dominance changes quickly. At Mars, sunlight is weaker. At Jupiter, it is already dim enough that the giant planet lives in a colder, slower light. At Saturn, sunlight feels even more distant. At Uranus and Neptune, the sun is still the brightest star, but no longer the overwhelming presence we know from Earth. Go farther, toward the Kuiper Belt and beyond, and the solar system becomes a place of twilight objects, icy bodies, and long orbital silences. The same star is still there. It has not failed. But distance has changed the experience of its light. This is a simple local version of the cosmic story. Light can be powerful near its source and nearly helpless far away. The universe is not dark because stars are weak. It is dark because space gives their light so much distance to cross. A candle in a small room can fill the walls with glow. A candle in a desert becomes a point. A candle in interstellar space becomes almost nothing unless you are very close. Stars are far more powerful than candles, but the universe is far larger than any room. That imbalance is one of the quiet reasons darkness wins. There is always more space than flame. There is always more distance than any one star can dominate. There is always more time than any one generation of light can last, and this makes every visible thing feel temporary. The sun looks permanent because human lives are short. The Milky Way looks stable because civilizations rise and fall inside a single instant of galactic time. The night sky looks mostly unchanged because our recorded history is brief. But the universe is not frozen. It is a slow process seen from a fast species. The darkness is where that process becomes visible. It shows what is not currently burning. It shows where light has not arrived. It shows where matter is too thin, too cold, too hidden, or too far away. It shows where the past has faded and the future has not yet produced anything bright. In that sense, darkness is not passive. It is the visible shape of cosmic timing. There is a quiet beauty in that, but it is not a comforting beauty. It is the beauty of standing near the shore at night and realizing the darkness ahead is not just water. It is depth. It is distance. It is a place where sound fades and vision fails long before reality ends. The universe is like that shore, except the ocean is not made of water. It is made of time, expansion, gravity, radiation, matter, and all the things we still do not know how to name. For now, our small world floats inside that darkness. The sun lights our days. The atmosphere scatters blue above us. Cities hide the stars from many people. But beyond all of that, the larger night remains. It was here before Earth. It was here before the sun. It was here before the first star burned. And it will still be here when the last familiar lights have faded into cold remnants. The universe is dark for a reason. It is dark because it had a beginning. It is dark because light is finite. It is dark because space expands. It is dark because matter gathers into islands instead of filling everything evenly. It is dark because most matter does not glow. It is dark because our eyes are limited. It is dark because horizons exist. It is dark because the future is not filled with endless new stars. And it is terrifying because each reason points to a deeper truth. The universe is not made to be fully seen. It is made of things that appear, things that fade, things that hide, and things that can never reach us. We live during a rare age when enough light still arrives to let us understand the darkness around it. That may not last forever. The cosmic microwave background will continue cooling. Distant galaxies will continue slipping away. Star formation will keep slowing. The bright era will become a memory, written only in remnants and radiation. But right now, the sky still gives us clues. Right now, darkness is not complete. Right now, the universe is still readable. And perhaps that is the final strange gift of the night. It does not show us everything. It never could. But it shows us enough to understand that the darkness itself is part of the story. Not the end of the story, not the absence of the story. And once you notice that, the night above you becomes less like a ceiling and more like an unanswered measurement, stretching quietly in every direction, the frame around every chapter the universe has ever written, in light.